So welcome, ladies and gentlemen. It's my pleasure to open the this month's Melo lecture, and it's even my greater pleasure to welcome Professor Satyam Suwas, who has kindly accepted our invitation to address our online audience. Satyam Suwas is a professor and currently chair of materials engineering at the Indian Institute of Science in Bangalore, India. And he obtained his PhD in materials and metallurgical engineering from IIT Kanpur and worked at various places among the Defense Metallurgical Research Laboratory in Hyderabad, University of Lorraine in France, and RWTH in Aachen in Germany, before returning to India and joining the Indian Institute of Science. His specialization includes materials processing, crystallographic texture, and mechanical behavior of materials. So I have spoken more than enough. It's my pleasure to pass the word to Satyam. Please, the floor is all yours.
All right. I think I have to share it again, I suppose, isn't it?
Yes.
Yeah. Okay, let me share it. There's some problem in sharing. Okay.
Let me check here. Advanced sharing options. All participants can share. Yeah, suddenly it's finished sharing.
Okay, so what I will do is I will come back again.
Okay,
right.
You can, okay. You leave us for a moment and you come back. Okay, I will pause the recording just a moment.
Right, it works, yeah.
This meeting is being recorded.
Okay, so shall I start now?
Yeah, please, you have the word. You can start.
Right,
Please.
okay. Okay, so first of all, thanks, Leo, for inviting me for this seminar series. I saw many who is who in the audience, so I'm a little cautious now. So, so this work which I'm going to present is a PhD work of one of my recently graduated students. And we have been working on this topic for quite some time. But before I go into the actual talk, there are many people who have not come to Bangalore. They don't know about it. So I will just show them that this is a map of India. And we are located here in southern side of India. So here the arrow points here and quite far from Delhi. So, and it's a very peaceful place, nice green place. Our university was established in 1905. So it's more than 100-year-old. And this is the aerial view of the university from the top, right? And in this university, we have our Department of Materials Engineering, which was established in 1945 as Department of Metallurgy earlier, and was renamed as Department of Materials Engineering in 2006. We are primarily a graduate school with 120 PhD students and 50 master students, including all years. But we also have a small bachelor's program where typical strength of about 20 per batch are admitted. And these are very smart guys. They are trained to do research from the beginning. And so past 2 years, when they come to the department, it's about 20 and 20 per batch. We have about 27 faculty members now in the department, and we publish, we're publishing, and incidentally, this has not dropped so much during COVID. So we publish about 200 papers per year, and we have about 40 to 50 academic visitors per year. This has dropped substantially, but hope to revive it. Just wanted to show that we love to have visitors coming to our department, right? And in the department, we have laboratory for texture and related studies, which was established in 2005 when I joined. And we work on various topics that is related to texture. We do not work on completely deeper aspects of texture. We do work, but we also work on applied aspects of texture, where we apply texture and processing science concepts. Like one of the major thing is severe plastic deformation. We work on all the materials based on the funding that we get. And currently we have about 16 PhD students. Of course, some are co-supervised by other colleagues. And we have 2 postdocs and 4 master students in the department. With this short introduction, I'll come to the topic. So what is dwell fatigue? What do I mean from dwell fatigue? Is when aircraft just does, it takes off, and then it does cruising for a certain time, and then before that it lands. In between, there is a certain time in which it is subjected to certain amount of stress, and this cycle is repeated as the operation of aircraft goes. And then this holding of aircraft at this level of stress actually leads to quite a lot of interesting phenomena, which are not very interesting from user point of view, because it leads to some amount of degradation in properties of the material and components, and therefore we have to find out the reason for this. And this was known for a long time. In fact, in 2003, a comprehensive paper was published by Professor Bashe from, I think, from England, and he has given a complete comprehensive analysis. But this was a phenomenological analysis. Later on, many investigators have associated this phenomena with crystallographic attributes, also to textures. And then therefore, many people got interested in it. Many texture people got interested in it. And then we went to, then we also got interested, and the intensity of work has increased ever since EBSD techniques have become more common. And this phenomena is seen in many metals. First, it was reported in metal 685, which is also known as, by RMI titanium, it is known as IMI 685. And this is observed at 20 degrees Celsius. That means at ambient temperature. And one main reason for which is attributed to this is room temperature creep in the system. And then this was investigated for various alloy systems, because this alloy is a high temperature alloy and used in particularly in this zone of the aircraft, particularly about below 600 degrees. In this zone it is used basically in compressor section and fan section of the aircraft, lower side of the compressor section. So the main thing is one of the most candidate materials for high temperature applications, or for high temperature applications of titanium alloys, is called titanium 6242 alloy, which consists of aluminum, zirconium, and molybdenum other than titanium. So this has, incidentally, though it qualifies for all other good aeronautical properties, but it has a very strong sensitivity towards dwell fatigue. So dwell fatigue debit is a kind of a parameter for the early occurrence of fatigue damage, and it is maximum for this alloy. But once one adds some more alloying elements, basically molybdenum concentration is increased, then it becomes it becomes saturated, but still there is a dwell fatigue observed in this material, right? So there has been, as I mentioned, there have been very many investigations on this. And one particular thing that has been found is high strain rate sensitivity gives high dwell sensitivity. And if there is a low strain hardening in the material, then it leads to high creep sensitivity. In both the cases, it is damaging in terms of occurrence of damage in the fatigue. So with this, now we wanted to investigate how does the in-plane anisotropy in mechanical property affect the dwell fatigue response. There is a reason behind it, because if we just see here is the yield stress versus applied strain rate uh, response of a material, a titanium material, which is generally basal textured in hot roll condition. Basal texture is substantially different along rolling and transverse directions. So, and this happens at almost at all the strain rates. So therefore, it was observed that this property is definitely sensitive to, or the dwell fatigue response is sensitive to texture of the material, right? Also, the strain hardening rate is in titanium is sensitive to the direction in which we take the sample. Again, it's a function of texture. So we can see that along rolling direction at 45° to rolling direction and at 90° to rolling direction, we have different responses of strain hardening rate versus true plastic strain. Now, we wanted to examine one by one many reasons that would lead to this dwell fatigue response, so that one after other some remedial can be recommended for this material. So the first thing is in-plane anisotropy. That is one that we wanted to see. And the one particular thing that we have seen is if we take titanium from the microstructure of titanium, and we carry out the deformation here from region to region, we see that there is a difference in the sliding of grains. We can see it here. There is a difference in sliding of grains in these materials. So this was considered as a phenomena that also depends on grain boundary sliding. So this is one reason. So first is strain rate sensitivity. Second is anisotropy, that means the texture. Third is the propensity of grain boundary sliding. And then this again is a function that is sensitive of the direction and the texture of the material, right? So now the question is whether the deformation heterogeneities play any role in the dwell fatigue of titanium, because the heterogeneities we could see here very clearly. And also we wanted to examine whether these variation in the degree of heterogeneities with sample direction has a consequence on dwell fatigue response. So this was a very comprehensive work done by Adam Pilchak and Jim Williams, and they just examined the dwell fatigued sample, the fractography of dwell fatigued sample, and they found that most of the grains where fatigue crack initiation has taken place, they are very close to basal, right? So here, particularly in this case, we could see this is various cases this has been examined, and almost all the orientation of grains where the dwell fatigue has initiated, fatigue cracks have initiated, they are primarily close to basal orientation. May not be exactly basal orientation, but very close to basal orientation. Like for example, here it was identified to be 10/17 orientation, right? So the theory behind this has, so far the knowledge that has been generated was, the first model is straw model, and straw model says that well fatigue cracks will initiate when a soft grain meets a hard grain, right? And in that case, the fatigue crack initiation takes place because of the pileup of dislocations at the boundaries of the hard grain, right? And again, there has been several other investigations, and I would like to mention one particular thing which came from Metz. The Lionel German and Nathalie J, they have done this work on IMI. If I remember correctly, it was done on IMI 834, right? And they identified the material which was prone to dwell fatigue had very strong macro zones. So again, this validates the straw model that wherever there is a strong basal orientation, and it is also said that the basal grain should be surrounded by non-basal grains. So in that case, there will be macro zones forming, and this could lead to dwell fatigue debit, means the propensity of reducing the life under dwell fatigue loading conditions. So these are some of the available knowledge. So we just wanted to examine this systematically, and first we went to investigate in-plane anisotropy of dwell fatigue we just took CP titanium, because again, since the alloy, there has been some varying response between different alloys, and the phenomena that has been explained, or all the theories just deal with HC phenomena related to HCP titanium. So we wanted to exclude all variables, right, including the presence of beta phase, which occurs in alpha beta titanium alloy as seen in most of the investigations. So we just took commercially pure titanium and examined the fundamental aspects of dwell fatigue propensity. The first of all, the anisotropic aspect. So we took a plate of CP titanium, which was obtained by cold rolling and annealing, and nice equiax grains, very fine grains were there. Grain size was about, say, 5 to 8 micron in most of the cases, and it has a split basal texture, which is very common in titanium. TD split texture is common in titanium or any hexagonal materials with C by A ratio or axial ratio less than critical. So this was observed, and then this material was taken further for further studies, right? Because this combination, according to us, would lead to high sensitivity for dwell fatigue. So, and since CP titanium, in CP titanium, it's easy to generate very strong basal texture. So we generated, and then we did the test of this material, and here is the result. So this is the loading cycle that was employed, right? So we have just done normal, in order to have a comparative idea, we just did normal fatigue with this kind of a profile, right? So one loading and then unloading, loading and unloading. While in the other case for dwell fatigue condition, we loaded it after loading, we kept it at that load for 120 seconds for 2 minutes and then unloaded it, right? And then again, the second cycle starts in the same way. So this is the normal fatigue. What I will refer to is the normal fatigue, and this we will refer to as dwell fatigue, right? And then we just, the strain versus cycle very clearly said what was at least anticipated from indirect responses about anisotropy is the material which was extracted along transverse direction had shown dwell fatigue sensitivity in this manner, right? So this has accumulated very high amount of strain in a very short cycle. And for this along rolling direction, we could see that the number of cycle, the strain accumulation versus number of cycle follow this trend. Under dwell, under normal fatigue also, this was similar. Only thing is the degree was a little higher in the case of dwell fatigue compared to the normal fatigue conditions. We did some normal tensile tests, and we just we monitored along the mechanical property along both the directions, and this was the response. So the TD material has shown a lower strength and ductility if it was compensated with the yield strength of the material. And similarly, so we also calculated the strain rate sensitivity, and we have seen that the strain rate sensitivity values were slightly different in both the cases, and only slightly. So it was lower along the case along rolling direction, and this has in one case it was rolling direction sample has shown high dwell fatigue resistance, while they also have shown high monotonic strain hardening. So this was the one which we saw. And then we examined the formation of texture in this material. So the way these grains hardened, or the way the texture evolution took place after subjecting them along deformation along rolling and transfer direction, made a contrast here. So here, for example, for the sample tested along the sample extracted along transverse direction and subjected to tensile test, has undergone stronger changes in texture, or has a kind of textures which are slightly different from the one which was along rolling direction, rolling direction tested sample. And then we could see here the changes in the texture could be seen here. Like tensile, the rolling direction samples are there under tensile sample, they accumulate strain over here. They get oriented mostly after tensile test along 10/10 direction, which is expected. And in dwell fatigue, they also accumulate strain along this direction, but under normal fatigue, the texture seems to have weakened. And the TD direction sample never acquires any strong texture. So we just examined the slip response along these directions. So basically Smith factors were calculated, and basal and prismatic and pyramidal, these three are important slip systems in hexagonal material. So we calculated the slip response along for all the three types of slip, and we could see that slip responses were different, right? For example, for basal slip, we could see here, I'm sorry about this, but this is the figure that has been provided to me, has a very small numbers, and it says that the fraction increases, the minimum increases from red to blue. Right. So that means the red, if there is more red here, that means there is maximum value of Smith factor is for these cases, right? This is the maximum value of Smith factor. So that way the responses were different and mixed for all the cases. Here it's more clear, extracted from the same data, where we could see that the average Smith factor for basal slip was lower for a rolling direction sample and higher for transverse direction sample. And similarly for prismatic slip, the order was reversed. And for pyramidal slip, it was almost similar with a little bit of difference, right? This was also subjected to investigation. The prediction of strength was, or a strength anisotropy was carried out by Dusseldorf originated software, the Damask, which almost everyone uses now. And particularly this part of experimental scan from EBSD was used. This is enlarged here. And then we have we have used this simple phenomenological power law, considering all the three types of slip systems. And we calculated for the inverse pole figure, and most important, the stress strain curve was calculated here after deducting yield strength. And we could see the differences were almost in the same order, except for the fact that the saturation has occurred much earlier with simulation, and a little bit of deviation from experiments could be seen at higher strains and lower strains, but the curve passes through this, so this much deviation is expected. Now, the prediction of activities of slip systems is seen here. So for RD loading, there is higher prism and low basal slip activity. And for TD loading, low prism slip and higher basal slip activity. And this is also to be noted that titanium also shows anisotropy in stacking fault energy. So the hardening behavior is also influenced by anisotropy of stacking fault energy, because on prism plane, the stacking fault energy is about 150 millijoule per meter square, while on basal plane, it is 300 millijoule per meter square. So it's as good as we are working on different materials if we consider FCC type of situation. Right. So after that, we could predict this the activities. The slip activity maps are shown here. So for RD samples, the basal slip activities are shown here, right? So the propensity of a particular slip activity is shown through this scale. So highest one is red. So here we could see some hot spots here, red ones. And for prism slip, obviously it is inverse of it, so it's minimal here. So it is basal dominated thing here, the red one. And then similarly for TD case, the trend was different. For basal, it has shown more hot spots here and there, all these cases. And then prisms, TD prism slip has shown again lots of hot spots here, higher propensity of Smith factor, higher propensity of Smith factors here. Then what about fatigue simulation? So these are under tension tests. In fatigue tests, what we have seen here is if the predictions said that the RD is the RD samples have lesser strain accumulation, as we could see, and the TD samples have higher strain accumulation. And this correlates with the basal slip and prism slip activities here. So the square and the circular ones, the square and the circular ones are for RD, the top one and the bottom one for RD, basal and prismatic slip, while the two types of triangle, inverted and rectangles, indicate for TD type of samples. And this was predicted, and the microstructure was generated like this. So we could see here that here in the case of TD sample, there is a lot of situations where we have heterogeneities that have come in the material, right? Compared to the RD type of situation where we have large number of grains do not accumulate strain. So this change in color is a clear indication of the strain accumulation in this case. And so this fatigue tests were also modeled, and basically the strain hardening, all kinds of modeling was done for strain rate versus strain for under these cases. And we could see almost a very similar situation as in experimental cases. And of course, we could also see the strain rate sensitivity values as per our anticipated, as per whatever we experimentally calculated in that line. So with this understanding, we could summarize this part particularly is a larger planar anisotropy is observed in dwell fatigue response, and definitely it is anisotropic, and dwell fatigue life is higher for along RD than TD, and a strain rate sensitivity is lesser in the case of RD than TD. Strain hardening response is higher in the case of RD than TD, and activity of prism slip is the one which is more in RD and TD, and that is responsible for intrinsic strain hardening of the material, and that is also accounted for accounted for the difference in stacking fault energy. And therefore, this whole thing clearly tells that texture plays a crucial role in controlling the dwell fatigue behavior. So basically, we have not changed different types of texture, but we have just extracted samples along different direction, which essentially represents two different types of textures. Particularly, the planes are same, but the directions are different, and therefore it indicates that the dwell fatigue phenomena is texture sensitive. Now, the second part of this presentation, I am going to deal with deformation heterogeneities and how does it affect the dwell fatigue of titanium. Now, this is a stress strain curve. This is repeated here for this material, and here we did some kind of a slip trace analysis for both these materials along the materials tested along rolling and transverse direction. And to our surprise, when we examined this, the deformed microstructure, these were very well electropolished samples, and we did some profilometry kind of thing, and we could see differences. We could see the formation of ledges along the grain boundary. Like in the case of RD samples, we could see that the grain boundary are looking very normal, while in the case of TD sample, we could see ledge formation. So this is also a function of direction in which we have extracted the sample, and very clearly we could see that there is a substantial difference in the grain boundary fraction consisting of ledges between RD and TD samples. So it's almost 4 times more number of ledges were observed in the case of TD samples. This was roughness of the sample was also measured. All were polished initially to the same extent, but we could very easily see that the TD samples were more rough than the RD samples. Well, so for these two samples, we also measured C-axis deviation, elastic stiffness, and prism Smith factors, right, which was considered as accountable for the dwell fatigue response. And we could see here that there is substantial difference. The roughness, particularly in this case, is about 27 and 34, so about say 20% or 25% difference in between the two. And there is a difference in the nature of the materials, the prism Smith factor here. Again, a similar investigation was done in the previous case also, but in this case, we completed the whole investigation on one sample for which we have measured these microstructures, and we could see that there is a difference in the trend observed between RD and TD. Right. So we just saw that we just tried to measure the CAM for these two samples, and there is some difference in CAM values, kernel average misorientation values from the EBSD maps between the RD and TD samples. About 25% difference was very clearly observed, and we could see here that in TD samples, as we also evidenced earlier, that there is a strain accumulation right at the grain boundary, and therefore there is a larger misorientation in along certain grain boundaries. So almost we can look through this and see that all these changes in the values of CAM values are very apparent near the grain boundaries, right? So basically, we all know that grain boundary affected zone uh, has more number of slip systems active over there in order to have the compatibility with another grain. So therefore, it is quite expected, but the degree was totally different, or degree was different in both the cases, right? And then we could see that in this case, we also measured the slip traces, right? So despite low Smith factor, in these cases, for example, the activation of the slip trace analysis was carried out. These are the experimental slip traces, the dotted ones and black ones, right? And then this is the prism plane trace plotted here, the red ones, and we could see that, that there is activation of multiple slip systems. From here, we can see, despite of the low Smith factor of the deformation for the prismatic slip, and this points towards local incompatibility stresses in the material. And we also did transmission electron microscopy to see whether the observations that we have had by EBSD and CAM analysis are true or not. And we could indeed see that in the case of the TD samples, there are some accumulation of dislocations here at the interface, which was in EBSD reflected by uh, higher CAM regions. To account for the local accommodation mechanism, we tried to see that whether this would lead to a grain boundary sliding, because this dwell fatigue phenomena is related to the room temperature creep of the material. So we wanted to see whether there is an element of grain boundary sliding here. And then what we did is we just did the standard marker method. And after deformation, we saw how much the markers have deviated. So this is, we could see here, this region and this region, that there is a clear evidence of grain boundary sliding in this case. And we have just we have seen that the strain was calculated for grain boundary sliding by this method, which is a geometrical factor, which is given in this formula, and the strain for grain boundary sliding is given here. And this also have a slight difference between almost not slight, it's almost double for the case of TD than compared to RD. So again, further confirming that textures have to play an important role. Then we examined now we going back to Stroh model for soft and hard grains, and also the misorientation between two grains. We try to examine the incompatibility between the grains, and we use this Lusters and Morris criteria for defining whether the slip planes, a particular slip plane, is incompatible compared to the other slip plane in other case. So this was measured by a parameter called M prime as given in Lusters and Morris paper. And these are the two angles, cos alpha and cos beta. Alpha is this angle and the beta is 180 degree minus beta is this. So we just measured the slip plane compatibility here, and it was given as a criteria that if this M bar is more than or equal to 0.7, then the boundaries are compatible, right? So we also examine the compatibility of all the grain boundaries with respect to C-axis deviation, grain boundaries with ledges and without ledges, all these things. And here is the result. So we could see here that the scatter is quite substantial in this case. C-axis deviation, if we could see here, this is in degrees, right? And the square ones indicate grain boundaries without ledges. And the red dots indicate grain boundary with ledges. Here, if we consider delta E, change in elastic modulus for these cases, we could see that there is more scatter with ledges, and the grains which have exhibited ledges at their boundaries compared to the ones which have shown no ledges, right? And similarly, the M factor is also lower for the case of grain boundaries with ledges compared to. So these are basically, if we go back, we could see that the higher, if it is higher, then it is a compatible, higher than 0.7, then it is compatible boundaries. So the zero point 0.7 is the criteria here, and it is, so in this case it is compatible, in this case it is not compatible. So this is also fitting very well with our concepts of ledges and all that. And then we thoroughly examined the samples more carefully, and this time we saw the cracks, and it was like catching a fish in a sea. And then we have just seen that there are cracks quite obvious in the case of, or more more frequency of cracks in the case of the TD samples along the grain boundaries, right? Then of course the pole figures indicated for the TD samples, the pole figures are just rotated by 90 degrees in this case. So the summary of this part of investigation is deformation is extremely heterogeneous with significantly higher extent of grain boundary affected zones and grain boundary sliding when deformed along TD as compared to RD. And the boundaries with a geometrical compatibility factor M prime lower than 0.7, and the delta C, that is the angle between the adjacent grains greater than 20 degree, are incompatible boundaries. The number of such boundaries are higher when loaded along TD. Therefore, it is more prone to dwell fatigue situation. And since there is a higher heterogeneity of deformation, the TD samples show low strain hardening, high strain rate sensitivity, hence low dwell fatigue life. That means they are more prone to dwell fatigue. They are not good as far as the application point of view are concerned. And then this is also shown that basal texture is less prone to anisotropy and deformation heterogeneities and is suitable for design against dwell fatigue. And the split RD and split TD type textures show anisotropy in heterogeneity, hence have higher sensitivity to dwell fatigue. So this was also a conclusion. Now, what is the crack nucleation mechanisms? So far, we have seen in what conditions cracks are forming, under what situations of grain boundaries, what conditions of Smith factor, what conditions of orientation. We are getting a situation that leads to crack formation. Now, crack nucleation mechanism. So for this case, we switched over to the actual alloy. We had enough data or enough experience with CP titanium, and then we took a real alloy from the funding body, that is Indian Defense Organization. So we took this alloy, that is IMI 834, which is so far the highest temperature alloy for used in gas turbines for titanium. And we just did some heat treatments. This is a standard heat treatment given before this is being used as a forged disc or turbine blade. Generally, it is used for discs. It's a disc alloy. So we have just carried out the disc deformation and annealing, basically annealing, and that generated this type of a texture. So we can see here that this is from it's a very weak texture, weak basal texture, and fully equiaxed microstructure. Because initially we wanted to gather an information where this beta phase, which is seen here, should not intervene in our interpretation, so that we can get a pure information about just the orientation and alpha-alpha boundaries. But in alpha-beta alloys, we do not generally see alpha alpha boundaries. Generally it is alpha beta boundaries that we see, because beta has a very high propensity of formation at the boundaries of 2 alpha grades. And again, this sample was subjected to a similar type of cycle as in the previous condition. And then we have seen that this was the normal fatigue and this is for dwell fatigue. We tested it at two levels of yield stress. One was at 95% and one was slightly over the yield stress values. There is a reason for that, and that will come later. This is basically the test protocol for this alloy. So we followed that. And we could see that for, let's see, first 95% loaded samples. Again, we compared for one particular sample. Here we have not taken the orientation aspect. We have just taken the as received sample, and we could see that there is a difference between dwell fatigue response between and normal fatigue for this both 95% of yield strength loaded sample, as well as the difference becomes far more if the yield stress increases substantially higher than the loading stress is higher than the yield stress. And then we cycled it, and we could see that the number of cycles to failure, NF, is for 95% dwell is 4,193, while for normal fatigue it is almost double. So dwell fatigue debit is 2 here. For higher loading stresses, the difference is quite substantial and it becomes 10 times. So that means the damage accumulation is higher in the case of if the loading stresses are higher, but again for it is much more in the dwell condition than the normal fatigue condition. So this is a very very interesting thing. And here we just saw where the cracks originate. So we did a thorough investigation of the origin of crack. So for example, this is the fractograph that we examined, and here it is the crack initiation region was found in the cyclic case, 95% deformed material. And we could see here, we could see here in both the cases, the faceted initiation we could account for. The magnified regions clearly say that there is a faceted initiation region and fibrous propagation region for normal fatigue tested samples, while here in this case in dwell samples, this is the region of initiation of crack in the center, right, in this case. And we could see that there is a faceted subsurface crack initiation with multiple crack initiation points. So all these things are pointed with red here, right here. So these are the crack initiation points, and it's also indicated as a ridges, all these points. So obviously the damage for the same amount of loading stress, the damage is more in the case of dwell fatigue loading condition. And a similar situation we could see for higher loaded samples. And here you could see there is a fracture surface you could see here. So in this case, in fact, if we have just taken the dwell fatigue samples with higher load, we couldn't even, it's so fibrous that we couldn't identify the crack initiation regions. In this case also, it was very difficult to see. So, but this is for sure that there is a difference, right? We also polished the sample and saw the crack formation, right? So again, for cyclic condition, if we consider load as a parameter, we could see here that there is more cracks, more propensity of cracking or crack initiation in the case of higher loaded samples. And for dwell, again, for the same load, dwell shows more number of cracks. So this is a very clear observation. We analyzed these cracks carefully and we saw the orientation. These were subjected to EDST investigations in those regions, very carefully picked up, and then we measured this. And we could see that for the dwell subjected material for 95% loaded, we see that the cracks, some cracks were having far from the basal orientation, but while there are most of the cracks were at some within 40-degree range of the basal orientation, right? So, and in this case, of course, this was quite spread. The crack initiation for higher cyclic loading was very strange in this case. So then we try to model it with Stroh model, whether this soft hard grain combination works or not. So particularly this orientation was seen here, and you see the slip traces were examined, and this is particularly a crack, right? So these grains G1, G2, G3 are mapped here in the pole figure. So G1, G2, and G3, we could see here very clearly that the C-axis deviation for G3, between G3 and G2, there is a separation, right? The crack is between G3 and G2. So we could see here that 50 and 15, right here. In this case, the C-axis deviation, elastic modulus deviation, and we could see other things, right? So it was very clear that so here we have used all our accumulated knowledge so far, the use of parameter M, C, E, and also the slip propensity of prismatic slip. So we could see that in one type of situation that the hard soft combination indeed works, and the Stroh model is valid in this case also. And right. So crack nucleates on the basal plane of hard grain, which also coincides with the plane of maximum normal stress. So this was the now, the other combination, other crack which was examined, again G1, G2, G3 here. So where we have soft grains, we have measured. There was some, as I said, that there were some cracks which were seen between soft case also. And then in that case, the crack plane coincides with the maximum normal stress plane, and this is the basal plane. So here the conclusion is crack nucleates on a non-basal plane of soft grain, but coincides with the plane of maximum normal stress. So the second factor, it's a orientation as well as basically the Smith factor also is playing some role. Now the hard soft combination is also examined. And here, without going into detail, we did a similar kind of analysis that we could find that the crack nucleates on a non-basal plane of hard grain and do not coincide with the plane of maximum normal stress. Now, there has been some theory that all the observations which are related to orientation or any parameter which is not related to the combination of hard soft orientation could be misleading, because we see only one plane of observation. So if we see 3D microscopy, and we could see that whether at the grain in which the crack is initiating, what is the grain above this and below this. So this exercise was also done, and we could see here that again, even after examining three-dimensional microstructure by fibbing and EBSD, we could see a similar kind of a trend over there. And we also extracted the morphology of cracks, right? And this is what it is shown here, right? For all the cracks, we analyzed so many cracks, and a lot of data were generated in this case. So this exercise has led to the conclusion that the imposition of a dwell time leads to higher debit in fatigue life than that caused by increase in the load, that is 95 versus cyclic 95 versus cyclic 100, and 202 means over and above yield stress, versus cyclic 95 versus dwell 95. So this is dwell time is the main culprit in this case. And then higher load in combination with dwell time leads to voids and micro cracks at the grain boundaries. Higher loads without dwell and load with dwell leads to crystallographic and transgranular cracks, which we have just seen. And crack is nucleated along the plane of maximum normal stress caused by pileup in the neighboring grain, that is the hard soft and soft soft combination. And grains favorable for basal slip are found to be more amenable to crack propagation than those grains favorable for prismatic slip. So I think, do I have some, shall I stop here and start discussion, or shall I continue?
Well, yes, yeah, I think if we want to leave some room for discussion, I could suggest you to round up now. Yeah.
Right. So I just now I come in person. Right. So so I'm open to questions.
Yeah. So thank you, Satyam. So I'm going to stop the recording now.